Words of the day are resonance and natural frequency. Let's start with the idea of sympathetic vibrations. In fact, all objects have a tendency to vibrate in sympathy with other objects or with external vibrations. If something starts vibrating in the vicinity, nearby objects will pick up on that vibration. They'll begin to vibrate too. When in doubt, put your ear down against your desk and bang on it. See what you feel, see what you hear. Next vocabulary word of the day is natural frequency. Another fun fact, all objects have a natural frequency at which they're best suited to vibrate. Natural frequency depends on the object's shape or geometry and material composition. Let's check it out.
So this set of tuning forks here came in the same box from the same company. They're most definitely made of the same material. The only difference between them, as you can see, is the shape. One of them is the same shape shorter, one is the same shape longer. And they've got different natural frequencies. Here's how you measure the natural frequency. Simplest way. Hit it with a fork and see what sound it makes. Almost a perfect scale. There. Hit it, say vibrate, I'm not particular how, and it will vibrate at or around its natural frequency. These two cups are made of the same material, but they have very different shapes. As you can see, they make different noises, and it's much harder to talk about the beautiful, clear pitch, natural frequency singular for this tuning fork, which is expressly designed for the purpose, than from these guys, where the best you can say about them is that they make a noise. This is where the shape and geometry comes in. Short summary of a very, very long field of physics. If it's a shape you'd be happy to see in freshman geometry, you can probably find the natural frequency pretty easily. However, if it's a shape that you're not happy to find the surface area and volume of, probably the reason you can't find its natural frequency, singular, is that it's got several natural frequencies, plural, because it's so complicated. Here's a good shape, which is not terribly complicated at all. And unlike those plated cups, this is made from exactly one molecule. I never could have afforded a fine crystal wine glass like this. This is 100% lead oxide through and through. It's a much simpler molecule than glass, which is silicon dioxide arranged in a crystal lattice doped up with argon once every 8 molecules, and that's even before you get started on the impurities. But this is a fine lead oxide cup. It's made of circles and cylinders and spheres and things that you'd be happy to see in geometry class. Let's hear its natural frequency. Pretty nice, huh? Many thanks to Carol and Bob, whose wedding crystal this was, who let me have it for free because they were moving and all I had to do was pack it all up and take it away before the movers came. So, here, take the fork, give the glass a tap, up here, up here. There's a natural frequency. Tap it again. All right, same lead oxide. Tap it again, right up at the top. A little louder. A little louder. Keep tapping. Now tap it nice and loud. The notes changed. What gives? Why is this glass suddenly different now than it was before? We know it's different. It's got a different natural frequency. Pause the video. Consider a hypothesis, then press play to check. Well, the first hypothesis is obvious. We've changed the material. It used to be 100% lead oxide. Now it's a little bit more than half lead oxide and the other half Concord grape juice. So, of course, since it has a different material, it's got a different natural frequency. The other hypothesis, though, is a little bit more subtle. Look at what used to be in the glass and isn't there now. Okay, my dear Baker Bird, prihagatan and drink up. on Main. We can do a very similar demo with these pan pipes, nice copper pipes. They've got plastic rings around them so that they can indeed vibrate. You've got a similar issue. We've got two copper pipes, same material, same shape. See? The longer pipes have, what would you say, lower pitches or higher pitches? There's one. Now try the short end. Go on. So longer pipes have lower natural frequencies than shorter pipes. And check it out. Try again with the glass again. It's back to the same note that it was making before, now that the grape juice is gone. Something is there in common between these pipes and this glass. Let's talk about resonance for a little bit, and then we'll come back and find out. Now that we know that they'll vibrate, and that they'll vibrate best at their natural frequency, let's specify how well will objects vibrate in sympathy with other objects. Well, if something nearby is vibrating, an object will vibrate a little. But if something nearby is vibrating at or near the object's natural frequency, the object will not vibrate a little, it will vibrate a lot. And this is what we call resonance. Resonance is when an object simply goes crazy. If you're resonating, it means you're vibrating a lot because something nearby is vibrating at or near your natural frequency. The example I like to use is this. You're packing up from a convention. All your luggage is ready to go, and you and the rest of the team are walking through the lobby in the big New York hotel on your way back to the airport, and you hear the band in the ballroom through the closed door. Look around the classroom. You're going to see at least a third and probably more than half of the class, as the teacher makes this noise, going, go on, you know you want to. All right, that's not resonance. That's sympathetic vibrations. Granted, the vibrations are being transferred through several different media, including your mind, but the point is made. Something around, you can hear the beat, it's going on, and you're going to get a little down and funky, just a little. What if this isn't just any team you're going back to high school from? This is our 6-time world champion Model UN team, and you have just returned from picking up our 7th consecutive first place win. And you and the Model UN co-president, whom you secretly have a crush on, are just awash in congratulations and glowing with victory. And you have, unbeknownst to your fellow MUN co-president, the bestest promposal ever that you have just been waiting to stage. Come on, you're already in college already. You've just picked up your 7th first place win in the entire world, and while you're wheeling your wheelie bag through the hotel lobby, you can hear, through the open doors of the ballroom, the band is warming up for this afternoon's big shindig wedding. They are playing your song. The very song you were going to use for your promposal. And they are slaughtering it. They're so bad. They're so bad. What do you do? You know you want to. While Mr. Jacobs and Miss Kramer are tied up at the front desk, they can't see what you're doing. Come on, 7-time world champions. You're in college already. You have the plane tickets in your hand. What are you going to do? You know you want to. That's right. You're going to put down your bag. You're going to run into that ballroom. You are going to knock those clowns off the stage who think they can sing your song. You're going to grab the microphone and you're going to sing, I will always love you. And you're going to sing until your significant other dies of embarrassment and the cops come to drag you off the stage. That's not sympathetic vibrations. That is resonance. And that's the difference between resonance and constructive interference. If you're not dying of embarrassment yet, that's constructive interference. Constructive interference, one person sings la. Now,
2 people sing la, it's twice as loud. 3 people sing la, it's 3 times as loud. 1, 2, 3, it's simple addition. But unlike constructive interference, resonance can be tens or hundreds of times bigger and stronger than the original vibration. You may not even be able to hear the original vibration because the resonance is so much louder. The resonance takes something that you couldn't even hear and makes it so you could hear it across a crowded room. Resonance results in waves of huge amplitude building up. How huge? Let's see. In the equations for resonance, resonant force, resonant acceleration, you'll see a term in the denominator that shows the difference between the frequency of what's ever going on, the input frequency, and the natural frequency of the object that's doing the resonating. Specifically, it is the frequency of the sound minus the natural frequency squared, and it's in the denominator. So as the input frequency gets closer and closer to the natural frequency, you'll see waves building up. You can see here we're looking at 5 times the original amplitude already. But if the input frequency matches the natural frequency, if this minus this is truly 0 to an infinite number of sig figs, you're going to be dividing by 0. Look at that amplitude. That amplitude has the potential to be infinite, or at least as infinite as your 8th or 12th sig fig or whatever it is you have on the calculator will allow. Now let's take a look at those copper pipes again. What is it that's actually resonating? One of our previous hypotheses may have been the copper. Let's follow up on that. Why can't you hear an electric guitar unless it's plugged in? It's got the same strings. In theory, they could be made of the same material as an acoustic guitar, so why is it that the acoustic guitar sounds fine, but the electric one needs electronic amplification? What does an acoustic guitar or any other classical instrument here have that an electric guitar does not? Hint, it's not just the string instruments, it's the wind instruments too. Most wind instruments do not need to be plugged in. Why not? What is actually doing the vibrating? Press pause, think about it. Try a couple experiments around the house to see if your hypothesis is right, and then press play when you're ready. Ready? Here's my contribution. This is a shofar. My great-grandparents brought it home from Jerusalem in the 60s. It's made from a ram's horn, and as any wind instrument player will tell you, you blow it by sticking your mouth into the mouthpiece, not going like a Disney character, but going like the world's biggest raspberry. That is why, interestingly enough, my Mora D'Atra, my rabbi, despite being an incredible rabbi and the most wonderful spiritual leader a congregation can have, cannot actually blow the shofar to inaugurate the high holidays. He is a very dignified and dapper little man who'll be the sweetest, nicest person interacting with elderly congregants, getting down to play with the children, but he values his dignity over all. And when he was in rabbinical school, he simply couldn't manage to stand up on the pulpit and go to a congregation of 500 people, even if it was a graduation requirement. So, what do we hear? Do you hear the member of the clergy or the Baal Tokea going into the horn? Let's try it. What is it that's actually resonating? I guarantee it's not the sound made by my mouth. You heard nothing like it. What does this instrument have that the violin has, that the clarinet has, that the saxophone has, that the piano has, that the grand piano has more of, but an electric guitar does not? What is doing that resonating?
The hole.
Not the hole itself. What's in the hole?
The air.
The air.
like
is
the air
what's
in the
doing
flute.
the resonating.
This is a normal flute. And this sounds like, that's a basic B flat. If you have a piccolo, which is a smaller flute, it is about the size of, it goes about until about here. It is about this large maybe. That is smaller. There is less room for air in it, and there's less air in it, so it is higher pitched. If you have a larger flute, which they exist up to very, very large sizes, about my height, and are played, humongous up and down is the largest one, with the head piece coming out. There is room for a whole lot more in that, so it is deeper. And it makes a deeper sound. If I play a B flat on this, sounds like that. But if I take the head joint off and play basically the same note, it's a higher note.
So, going back to that geometry we were talking about before, here are all the different flute sizes. They're arranged from highest pitch to lowest pitch. Now, we can do something more specific than size. Which dimension of this flute is making the difference? What is controlling the wavelength and thus the frequency of the sound? Think of a hypothesis, pause, press play, and we're going to check. You got it. It's the length. That's what made the difference with the copper pipes. It wasn't that some pipes had more or less copper than any of the other pipes. It's that they had more or less air. The wavelength of the standing waves that's allowed open-ended in these tubes is directly proportional to the length of the air in the tube. The fundamental frequency with antinodes at both ends and a node in the middle is going to have a wavelength equal to the length of the pipe. Longer wavelengths have lower frequencies. Shorter wavelengths have higher frequencies. Set up a complete set, and when you have half as much length, you get half as much frequency. Or Physics in Action example number 1. Angers, April 1850. The bridge is perfectly fine. There's no weakness, there's no mechanical failure. But when a regiment of soldiers marches across the bridge began to shake violently and eventually collapsed into the river, killing over 200 people. Now, April 1850, if you're the Germans or the Italians or anybody else who's not thrilled about the French army, you call this an act of God. But if you're the French, you want to know what happened. The bridge was perfectly fine. Pause. Indicate your hypothesis, press play to check your work. You guessed it. Those unlucky soldiers were marching at the natural frequency of the bridge, one of its natural frequencies anyway, and the bridge began to resonate. Therefore, soldiers ever since then have been told to break step, stop goose-stepping, and walk like normal people if you're going across a bridge or any other physical structure that could possibly resonate. Just walk like normal dudes, and then you can start marching again when you're safely on the other side. Physics in Action, example 2. How can you break a wine glass with your voice? Well, Physics Expo 2019, Sean and Lucy say it's a lot harder than it sounds, but you have to do 2 things. Again, pause, write down your hypotheses. 2 separate things you have to do with your voice in order to break a wine glass with it. Check out the 2 examples of people doing this on the RZJHS Physics playlist that comes next, but we're going to turn in to the Harvard Natural Sciences lecture demonstration where they are playing sound from a generator at a certain frequency. Specifically, they're turning up and up and up their sine wave until they hit the exact natural frequency of the glass. You can see the vibrations in the beginning. You can see the paper that's on the rim of the glass start to move. But the glass is going to resonate in its fundamental vote of vibration. That's the first harmonic. And if we strobe just a wee little bit out of phase with the motion, we can see the nodes and antinodes. You can see the crests and troughs as they pass round and round and round the glass. Now let's turn that sound to a slightly different frequency. Let's see if we can match the natural frequency and do one thing that we're not going to do in the lab in person, and that is turn up the amplitude really, really, really high. Remember that resonant vibrations are hundreds or thousands of times stronger than the original vibration, but 1,000 times nothing is still nothing. Now, let's turn up that amplitude. Let's see if we can get that frequency to exactly right on one of those normal modes of vibration. Here we go. Let's see what this sounds like. There we go. There. Oh! Glass is not meant to vibrate like that. Stretch, crash. Next example of physics in action, the famous Tacoma Narrows Bridge. It was bigger, better, grander than the Golden Gate Bridge. It was the most amazing bridge in the country. It was the 9th wonder of the world, and it stood for 3 months before it collapsed in a gale. What happened to the Tacoma Narrows Bridge? Consider for yourself. The Tacoma Narrows are called Narrows for a reason. They're shaped exactly like the wind tunnel in front of our school. A big rectangle with high sides and a gap in the middle, a rectangle filled with air. Ask yourself, does a rectangle filled with air have a natural frequency? And if it does, what would happen on the extremely unlucky day when the frequency of the wind through that gap was blowing near the natural frequency of that giant rectangular prism full of air? The Tacoma Narrows Bridge had been nicknamed Galloping Gertie since opening day. It was known to do the most interesting things in high winds, and motorists used to drive across it on windy days for fun, like getting a roller coaster ride without having to pay for a ticket from the carnival operator. That is why you will see in the footage that there was a car on the bridge. The motorist fled for his life, and the one incredibly lucky cameraman who set up his video camera on that fateful day in 1940 when it was known from the weather forecast that a wind was going to blow, to observe what Galloping Gertie, the bridge, did in that wind. The camera operator got the entire disaster on film. That newsreel made his fortune. The camera shop still operates out of Seattle, owned by his grandsons, on the proceeds of that very, very successful cameraman. If you look closely at the official newsreel footage, which is up next on the RZJHS Physics playlist, play it and see. You'll see over the shoulder of the cameraman when he goes to rescue the dog that the extremely panicked motorist left in the car. I'm told that the dog was frightened out of its wits by the motion of the bridge and by being left behind, and it bit the man who came to rescue him. But nevertheless, you will see the man and the dog fleeing back to safety mere minutes before the bridge collapsed. Watch the official newsreel, complete with very dramatic 1940s music and an overexcited announcer. Then watch the next 2 videos to confirm your hypothesis as to why the Tacoma Narrows Bridge collapsed.